Okay. Yeah, people are we're starting to trickle in, and I'll get started now, and then we can let everybody else join as we go. So hi everybody. Thank you so much for joining us, and everybody can see the slides and hear me okay, right? If someone could say in the chat, just so we confirm that we're not having any technical issues. Okay, great. My name is Josh Mineroff, and I am really excited to get the chance to talk with you all about machine learning. Um, this is going to be maybe a little different than some of the other talks that you've seen at MLOps. So there's been a lot of really great deep dives already, and there are some more that are scheduled. For instance, my colleague Josh Poduska just gave one on AutoML a few hours ago. Some of you might have been in that talk. This is going to be a little bit of a different approach, where we're going to sort of cover the whole modeling process from a higher level, and then we're going to get down. And the goal is not necessarily to make you an expert in any specific thing, but to give you an understanding of what the whole process looks like. I find a lot of times when I jump into a new field, or anytime I'm learning a field, sometimes you start with pieces of really, really specific skills, and it takes you time to kind of build those all together to a holistic understanding of what's going on. So I'm going to try to, shortcut that process and get you right to having the big high level view of how all the pieces fit together. So with that, we're going to jump into it. So I said that my name is Josh Mineroff, and I'd like to take another moment to introduce myself. So I went to grad school at Iowa State for optimization and industrial design. And that's actually how I ended up at Domino. It was a really nice mix of the technical stuff that I had covered in my optimization PhD, and also the human side of things. As a field engineer, I get to solve a lot of user problems. So it was like a really great mix of the two of those. Our goal at Domino, which is where I work, and that's the platform that we're going to do this workshop on. The goal for Domino is to be a system of record for data science. And that means that we work with enterprise data science teams across many industries who are doing cutting edge work. And that gives us a lot of opportunities to see the best practices from across the process that go beyond just the technical aspects. So this talk is going to include a lot of those learnings. I'd also like to mention that we have some TAs and other people helping out from Domino in the chat. So if you run into any technical issues, just post in the chat and we should be able to get it figured out. A quick overview of the agenda. So there will be a hands-on component of this. So the first thing we're going to do is take a few minutes to get set up with the Domino environment. We're going to do that hands-on workshop in. Then we're going to come back to the slides, and we'll spend some time motivating the problem. So this is really important, and I want to spend some time to explain why what I'm going to talk about is such a big deal. Then as we go through the talk, we'll get more concrete into the actual workshop, where we'll do some hands-on stuff with an example problem, all the way from data exploration to publishing an app. And then there will also be a model competition, I'm hoping, within that workshop component. We'll see if we have time. And then finally, we'll wrap up with a Q&A. So the first thing that we're going to do is, if everybody can go to this link that's posted up here, and we can post a copy of that in the chat. I'm typing that in the chat too. This is the Domino deployment that we're going to use for the hands-on. So you may have attended Josh's earlier talk, Josh Poduska. And in that case, you may have already signed up with an account for this Domino. But if not, you can go to that link. There should be an option to sign up on the bottom. And you'll just create a username and password that you're only going to really need for this workshop. And once you log in, you should already see an intro to machine learning project. And now in a second, I'll click into, I'll switch over and I can show people exactly what they should be looking for. So once you've logged in, you should now see this Chrome page. Let me zoom in. Once you've logged in, then you should be able to come to this projects link on the side. You'll see all your projects. You may be here by default. And then you're going to go into this Intro to ML project. And this is an individual project that was set up for you by default. And if anyone's been able to get into this project, just let me know in the chat. And similarly, if you've had any issues or haven't been able to get there, let us know and we can help you figure it out. Okay, so it looks like people are starting to get in. So what we're gonna do now is we're gonna start up a workspace, and then we're gonna let this start up for all of us while I go through some of the content, and then we'll come back and actually get to play around in the Domino. So on the side here, if you click on the workspace page, what we're gonna do is we're gonna click on new workspace up here, and I'll talk for a moment about what this does exactly. So a workspace in Domino is basically an interactive session, like you might be used to working in any IDE on your local machine, except we do it all in the cloud. So you have some options here, right? You can give this a name, let's say, whoops, and you can choose a different hardware tier. So here we're gonna stick with the default hardware tier, which is 2 cores, but there's always these options to pick different size hardware that you want. And here we're going to use the default environment. And the environment contains all the software and packages that you need. And I'll dig into that a little more as we go on. You can use Jupyter or Jupyter Lab. I'm going to use Jupyter Lab. So if you want to follow along and have the UI be exactly the same, I would pick Jupyter Lab. And then you can just click launch. And then you may see a page come up with some different steps of pending, and that's fine. We'll go back to the slides. We can come back to that in about 10, 15 minutes. So just to answer some of the questions in the chat, so you should not need to copy the project if you were in the last workshop. The way we set it up was a little different. So this time, this is just your own, the copy has been the project has been pre-copied for you already. It's your default project. And I think Adetyan was asking if you need a specific set of credentials for the link, but here you'll just have to sign up and enter your own email and come up with a password and things like that and kind of create your own credentials. I'm going to move on. We'll go over this really quickly before we actually do the workshop again, just in case anyone else joined. So this was what we had just talked about, that a workspace is actually the interactive session in Domino. So now I'm going to take 10 to 15 minutes and provide some context on data science and machine learning. So the key thing that I'm going to start off by talking about, and it's what makes machine learning such a big deal, is this really innocuous sounding thing that's called a model. So the potential of a model is different than, maybe in the history of BI or data analytics, which was mostly about visualizing and then summarizing your data in lots of different ways like dashboards. What a model really does and where the power of a model comes from is that it lets you automate a decision-making process. And why do we care about this, right? So the reason that we care is that we've seen some of the most successful companies in the world are putting models at the heart of their businesses. And I'll go over a few examples. So some you may already know, right? Netflix, and Netflix uses a lot of different models, but one of their most powerful ones is their content recommendation model. So this is like when you're in Netflix, it shows up the recommendations for what to watch next and things like that. And that leads to more viewers and higher engagement. But they also use the same data and models to decide what content they need to create. So then they have even better recommendations to serve up to you the next time you go into Netflix. Maybe a little bit less known than the Netflix example, Coke actually uses a model to determine how they manufacture orange juice. And here they have some target flavor profile that they want the orange juice to meet. And they use real-time pricing, they use information on their supply chain and the weather to change how they're sourcing the ingredients to make sure they meet that flavor profile. So this helps with things like operational efficiency and profit margin, and allows them to be robust to smaller scale, availability changes in ingredients and things like that. And one more classic example, insurance. So models have been used for a long time and are pretty widely used to price insurance with with much more accurate loss models than was done before you had ways to do this automatically. And they're also, though, used for processing claims. So some companies will like let you take a photo of an accident on your phone, and then a model can analyze the photo and do a first pass prediction on what the outcome of that claim is going to be. So what this does is it gives you a better UX as a consumer, and it gives claims adjusters time to focus more on the complex claims. So I love presenting this slide. And the reason that I mentioned those examples previously is that we think that not putting models at the core of a business kind of sets you up for an existential threat. And what that threat is all the other companies that are leveraging data science across the organization. And this is because models provide two major benefits to how a business operates. The first is breakthroughs, which are really big leaps that allow you to offer new products or go into a new revenue stream. And the second is operational efficiencies, where you're using a model to slightly improve the way you were making a decision process or make it more consistent. And over time, that can stack up and become a really large competitive advantage. And I'm going to show actually Jeff Bezos's 2016 letter, or an excerpt of it. And here he touches on both of these. So these are two paragraphs that are actually taken directly from his letter in this exact same order. And you'll notice that in the first paragraph, he talks primarily about some of the really visible, like quote unquote cool stuff that Amazon is doing with models. Things like Amazon Go, where you can check out without a checkout line, or delivering things with drones. But he also touches in this second paragraph about how they use machine learning to even just improve the fundamental aspects of their business, things like fraud detection, which maybe don't sound as exciting, but can drive like really important operational efficiencies. So many of you were probably nodding along as you saw this. So we had actually done a survey of a bunch of companies in February back in 2018. And a summary, or a one-sentence summary of what we found, kind of gets to the core of what I really want to impress on you with all this talk about the motivation behind machine learning. And that takeaway was that even though a lot of people know that it's important, even if you are doing a lot of data science, you're still doing it and treating it as just a technical practice instead of an organizational capability. So think about things like marketing, software engineering, sales, right? These are all like organizational capabilities that, of course, they require specific skills and technical expertise, but they also cut across all aspects of a business. And doing them well requires that you have all the appropriate organizational wiring set up to get everybody involved, right? You need all the different stakeholders to be able to have input in those processes. And in our view, data science is no different. And elevating the role of data science beyond just technical aspects is what allows it to be so transformative to a business. So I'm gonna start to get more concrete now, and then we'll have all the fun doing hands-on modeling. But if you walk away, or if you close out of the Zoom, remembering only one thing, this is really one of the big takeaways that I want to impress on you. So what exactly does making data science an organizational capability mean? This is a very high level abstract view of what it can look like to do this well. And there's a few key things to take away from this. So first is the idea of model development. So this is what you typically hear about. We're talking about a model. Obviously, we have to be making those models. And what this looks like inside of this area is kind of an iterative R&D process. And we're going to dive into that a little more. So besides just making models, you want to actually be able to get them out there. The best model that's just sitting on your laptop isn't going to bring any value to the business. So you want to be able to take the work you've done and then actually go out and publish and deploy it. There can be a lot of ways to publish things, anything from an API that can be used to power other systems. You can have a web app that you use to power some consumer experience or interactive dashboards or things like that. So when you go from model development to actually deploying something, you're going to want to obviously have a lot of validation and review. And these are things like, how do we know that the model we're about to hand off some of our decision making to is safe, that it's going to work as expected? And this can include things like compliance. And then to close this loop, you also want to have some monitoring and feedback. This is an area where best practices are still kind of maturing. But the questions you're thinking about here are like, are how do we know that our models are performing as expected? Does the data that the model was trained on still represent the operating environment? Are we getting the ROI impact that we expected? And doing this whole iterative loop well and doing it fast will help you make incrementally more valuable models over time. I'm not going to dig into this part too much, but you also see many of the different stakeholders that are involved shown all around the loop. So a big takeaway of this is that you want to be doing this loop, but it also involves this tight orchestration across many stakeholders that are feeding into the process. And you want to approach it by trying to build empathy, not trying to finger point at different stakeholders for slowing the loop down. And technology, we believe, can help reduce a lot of the friction of this cycle, and that's one of the goals that we really aim the development of Domino towards. So now that we have all that context, we're going to focus mainly on model development. So I've talked enough about how important models can be, but kind of the last thing I want to touch on is that just quantity is not everything, right? You want to make sure that you're picking the right models to build. And one way to think about this is kind of the model myth, right? So there's this misconception that because models involve code and data, that they should be treated the same as software and data, but they're different, right? It's more of a research project as opposed to kind of iterating where you have really clearly defined deliverables in each step as more traditional software engineering. And here, this will expand on that a little bit, right? So with traditional programming, you have some data and you have a program and you put those into the computer and that gives you an output, right? So you can kind of deterministically decide what kind of program you want to use and where the data is coming from, and you design for that specific output. In machine learning, however, we're starting with data and the output. And what we want to get out of the process is the program. So that's where a lot of the uncertainty comes from, right? There's many programs that can give you a certain output and you're sort of trying to figure out the best one or the one that captures the behaviors that you most care about. So how do we think about these projects then if they're really hard to just directly structure? And the way you want to think about this is prioritizing on two axes primarily. One of them is the expected value of a project, and the other is the expected effort of a project. So you're not going to get exact on these. Obviously, the more you go through this loop, the better that you'll get as an organization. But you want to at least try to get an estimate of order of magnitude. For value, you care about how much improvement is realistic in terms of ROI or really core business outcomes. And in effort, it's how much work will this take to do this project. And with these two axes, you can build this basic scatter plot that you see on the right. And while this is order of magnitude, but this will at least make it easy to make business cases and discuss the ideas of specific projects with a little more transparent and a little bit more rigorous of a process than kind of having it all in your head of which project might be the right one to do. And obviously, we want to generally try to pick the low-hanging fruit of like these really valuable projects up here that are relatively low effort. Another thing that we want to think out is risks. So this is kind of a third axis. So there's gonna always be different risks between projects. This could be anything like the barriers to adoption. Maybe it's gonna be really expensive or difficult to get buy-in from outside of, from other parts of the organization to actually go get this deployed. Maybe there's a lot of risks if you put this model out there and it predicts something wrong. So you might choose to pick the less risky projects first, and there's nothing wrong with that. The idea of this, again, is that it helps you have an explicit conversation of, hey, we're going to do this big risky project, or we're going to do this small incremental project. And those are the kind of decisions that you want to be aware that you're making when you pick the next model to build. So traditionally, software and engineering projects have this concept of a product manager. And these principles apply just as much to data science projects, where you're kind of making trade-offs and determining what's going to meet the value of the business the most. Some other considerations before we really start to get deeper into the actual process of model development. First, you'll want to think about data availability. So before you build the model, you want to make sure you actually have the data, or you have access to the data that you need to build that model and train that model. One way this can feed into that loop is that you can use some data limitations. Maybe you couldn't do this project because you're missing a certain set of data, but you can feed that back into the engineering team or your data engineering team to make sure that you have that data so you could do that project in the future. You'll also want to review any prior art, internal and external, right? You don't want to only build on things that you've built in-house. And the way that looking at prior art really helps is you're effectively piggybacking off previous work and lowering the effective level of effort that's being done, or that is required for you to do your project. You also want to think about delivery. How are you going to deploy this model? And planning here is the best chance you're going to have to make sure the model will actually be used. So a lot of times you can go through this whole process, you build this model, it's super accurate, and then maybe it doesn't get used how you thought that it would be used, or it doesn't get used at all. So here is where you'll want to plan this out proactively, and you can do things like show different stakeholders maybe a mock-up of what the output would look like, and this can kind of help people get the creative juices going to figure out if you're solving the right problem, or maybe you need to pivot to a slightly different model than what you expected. And finally, I touched on ROI, but you really want to have clear success measures for any project. And this is just, how do you know that the project worked and that it was valuable? So even if you can't get an exact number here, you can do heuristics like survey different stakeholders, or look at some proxy metrics for what you actually care about, and try to frame this as close as possible in terms of actual business KPIs. And this can drive, like I said, this is sort of a little bit of a developing area in terms of processes and technologies. So this can definitely drive additional tooling as you try to close that part of the loop with tracking. So what is Domino? How does Domino fit into this? So on the left here, you can see kind of the main steps of a process of building and deploying a model. And what Domino is a platform that kind of deals with a lot of the dirty work in terms of being able to access resources. So you can go through and do this process without having to worry about headaches. Like many of us have had the experience where you go to run some code from 2 or 3 months ago, and it doesn't run quite the same. So Domino helps kind of handle a lot of those things and make sure that the work you do is reproducible and that it's organized, and you don't have to spend a lot of time dealing with infrastructure and things like that, as opposed to actually the valuable parts of building a model. And when we go into Domino, we're going to actually work in a workspace. So I wanted to give people a really quick high-level overview of what's actually going on behind the scenes. So what this is a terminology review for Kubernetes. So Kubernetes is one of the main technologies that Domino is built on. And what this does is allow us to schedule these things called Docker containers. And a Docker container is basically a standard unit of software with all the code and dependencies. So you can think about it using the analogy of maybe developing on your local machine. A Docker container is kind of conceptually the same as a snapshot of your machine at some exact moment in time. So you can go run a bunch of code and do some other things. And then if you reload that Docker container, it'll be exactly how it was before you ran all that new code and things. So this is what makes it really easy to reproduce your work. And what Kubernetes does is a Docker container is not actual hardware, right? This doesn't actually run your code. So you need to slot it onto a physical machine. And this is can be a server or a local cluster or anything like that. And Kubernetes takes all these Docker containers. So you say, hey, I want to start some new run or start some new modeling process. And it will spin up a Docker container, put it into one of these pods, and then it handles kind of all the scheduling dirty work to efficiently use any of the machines that you have available and slot all those workloads into the hardware that you have. This is a really high level view. We could easily do a 2-hour tech talk just on Kubernetes, but I want to at least, if any of you want to come away with having some idea of what's going on behind the scenes, make you aware of that. So now we're ready to really start diving into the actual model development process. So these are like kind of the core parts or subcomponents of the process. And you can see that after we get the data and we prepare the data, which can be really involved, and we're going to get into that with our hands-on, then building the model and evaluating the model is kind of this iterative, that's where the iterative R&D process comes in. Sometimes we may need to go back and get more data or prepare more data, but we'll dive into each of those a little more over the rest of this talk. We also, I've mentioned that a core value of Domino is making sure that we can collaborate, right? That if you have work just sitting on your laptop or a local machine, but it's not being shared with anyone, that's not especially valuable. So we have a lot of tools in Domino that help you collaborate and share what you're doing. And one of those that we're going to touch on near the end of this talk is taking the model that we build and then deploying that as an app. And you'll get to see how you can go from just having raw data to having an app that you can share with people and help them understand the results of what you did. All right, so now we're going to start diving into getting data. So how do I get data? This is a huge question, and you could see a list of just some of the ways that you can go and get data. A lot of the times you'll be either connecting to some existing database, maybe it's a company database, maybe it's a public data set. You could do web scraping, right? If you want to, this is the idea that you're going through lots of websites and getting different data off. Let's say you want to go look at rental prices, right? You might go through the Airbnb pages or Zillow or something like that and pull a lot of the numbers down from the website in an automated fashion. And you can also use an API, which is more of a universal translation layer between different software packages. So this allows you to reach out to Google Maps or any other services like that and directly request the specific data that you need. So besides knowing where to get your data from, you want to make sure that you get lots of data. And not just a lot of data, but you want to make sure that you have data that covers all of the features that you need to classify or predict whatever it is that you're hoping to find. For example, if we're hoping to classify images of an elephant, but we only have pictures of an elephant's tail, we wouldn't be able to do that very effectively. And we would need to pull in images that cover the entirety of the elephant to do that well. And you can see in this comic, right, some of the things that you might guess just seeing small subsets of the elephant. Many times getting this holistic picture requires that you use many data sources, and then a lot of the challenge is figuring out how to connect all of these different data sets that you have together. Here's another example of how choosing the right features can make or break your project. So in this case, we're trying to say from two features, are we looking at an apple or are we looking at an orange? You can see on the right that if we have ripeness and a number of seeds as our two features, you can't really separate which one is an apple and which one is an orange at all, just based on those. However, if we use weight and color, it allows us to draw this really nice line that kind of bisects with apples on the bottom and oranges on top. So this showcases a little bit how choosing the right data and the right features can really make your project successful. Once you have your data, one thing to make sure you do, and this is surprisingly can be overlooked because it may be difficult to get your data, and now you're so excited you have it, you want to jump straight into modeling, is you always want to sit down and actually inspect the data. And like this is directly looking at the data that you have. So you can visualize it, you can look at descriptive statistics, you can look at values that don't match or aren't the right format and things like that. And the final thing that I want to touch on is when you get data, always be aware of data bias. So when you build a model, like I said, you're automating a decision-making process. So based on, if you use bias data or you introduce bias into your data when you automate that process, the outcome of that process is also going to be biased. So here are a couple of cases of this. There's many news articles about this. And one really famous case recently was an algorithm used in the US to guide sentencing. And according to the analysis, they predicted that African-American defendants had a higher risk of recidivism than they do, and the reverse for white defendants. So this kind of like should really help drive home how important it is to make sure that you're not inadvertently biasing the models that you build. All right, so we're basically getting into the hands-on part now, and what we're going to do in this workshop is we're going to see if we can use publicly available data to identify potential surveillance planes. So some of the flight data that we have are radio signals, latitude, longitude, and altitude of the planes for over different points in time. And the goal is that we want to start with this public data and end up with an app that we'll be able to go and share. So now we're going to do some hands-on data exploration. I'm going to take 1 second in case anyone joined to just show them at least the link, although Josh Podeska just posted it. So what you're going to do is you're going to click on that link and sign up for a new account. And then you'll start up a workspace. And I can show you really quickly where that is in the UI, and then we're going to actually all switch over and do the hands-on component. So for anyone that just joined, once you sign up, you're going to come to this projects page. You should see an intro to ML. And then you'll come into workspaces, and a workspace is an interactive session, the same as an IDE or anything like that that you'd be used to using on your local machine or any other service. And then we'll start up a new workspace. And you here now, so right, the hardware tier is kind of, if just as a refresher, and since I touched on Kubernetes since last time I went over this, a hardware tier here, what we're defining is kind of the size of that pod that we want Kubernetes to slot into the underlying hardware. So here we're choosing the default, which is 2 cores and 10 gigabytes of RAM. And the workspace environment is that Docker container that I talked about. So this already has a bunch of the packages that we need installed, so we'll just be ready to go from that. And then you can pick Jupyter Lab and hit launch. And that should open up another tab that looks like this. So what we're going to do here, we're going to go into the first notebook. So on the side, and if you're in Jupyter, you'll see a slightly different interface. We're going to double click on this data cleaning notebook. And what this is a Jupyter notebook. So this contains cells that have either Python code or Markdown in them. And I'm going to walk through the notebook and kind of explain what this process actually looks like in practice. So if a cell does contain code, just make sure you hit Shift Enter, like while you're clicking inside the cell like this. And that will run the code in the cell, and that'll make sure that you don't have any errors from not running things in advance. So you could see here some more info on the background. I'm not going to go over this in too much detail right now. This is basically the idea for this project came from a news article where they looked at some aircraft transponder detections, and they took that data and tried to identify spy planes. So we're basing this off of some of the data that they had and some code that's also available on GitHub. You can see here some of the features in the data, and primarily these are things like the altitude, latitude, longitude, and the direction that the plane is heading in or has changed since the last one. So what we're going to do now is we're going to actually go and import our data. Uh, and this, I'm going to kind of step through this, and then I'll accelerate the pace as we go through, just for people who may or may not be familiar with Python. So what we're doing here is we're importing a bunch of libraries we're going to need to do this. And again, you'll click into the cell and hit Shift Enter, and you can see it changed from an asterisk to a number. That means that the cell finished running. So we have all our packages. What we're going to do now is actually pull in the CSV file with our data. So pandas is a library we're using to do this, and pandas kind of shows data frames, which look like this. And it's effectively a table, right? So you have rows and columns of data, and you can, the really cool thing about using packages is they automate a lot of this process, right? So you can see in just these 2 lines of code, we've pulled in all our data, and now we're able to actually look at the data. And we've pulled all our code into df planes, which is the data frame object that we're going to be using. And this head command just shows the first few rows of the data, and you can, do things, interact with the functions here. Like if you change this number, it'll show you more rows of the data. So now we're going to actually explore the data, right? Just having the data in here, we want to go look at it and try to get an understanding of what's going on. So a lot of people look at data with the head command in pandas, and this shows you the top few rows. But it's actually really nice to use this sample command, because this here you can see, we're just looking at rows 0 through 7. But in this case, we're looking at 5 random rows. So a lot of the times, maybe the top 10 or 20 rows of your data will be really clean, and you only start to see issues as you get further down. So this, you can increase this number, and this just makes it more likely that you'll see something anomalous inside of a row. You can also obviously look at the size of your data. So this says we have, just shy of 20,000 rows, and there's 33 columns where each column is a feature. And in this case, we can't fit all the columns on screen, right? There's 33 columns, and some of them are truncated over here. So pandas also has a way for you to really easily see a list of all the columns that are available in your data frame. And if you want to do some more descriptive statistics, besides just directly looking at the data one entry at a time, you can use this describe function, which will show you for each column of data that you have, things like how many entries there are here. They should generally all be the same, the mean of that column, standard deviation, and different quartile values. Pandas can also be used for more complex exploration. So here you can see we've stacked some of the different functions of pandas. We're looking at just this one column in the data frame of the type of plane, and we're looking at the number of unique values in there, and then we're going to kind of print that out in a nicely readable string. So here there's 455 different types of plane in the data set, and 2,500 records. We don't know what the type of plane is for those. Also, besides just looking at summary statistics like this, a picture's worth 1,000 words, right? That's how the saying goes. So you can also use different plotting packages to check for obvious patterns in the data. And here we're plotting a bunch of plots with 5,000 different points, so it might take a second. And what we've done is we've trimmed the data frame down to only include these different features. We're just assuming that those will be good enough for us to train the model, but in general, you may do a lot of work to do that trimming. And you can get this nice pair plot. And what this shows is the correlation between different features. So like this one, for instance, shows on one axis is the duration, and this one is the observation, or you could see kind of this entire grid of things. And on the diagonal, because it would be, duration and duration on the same axis, you just see the histogram of that column of data. So this can be a great way to see things in here, like if there's any kind of correlations. This data set actually doesn't have a ton of correlation. Maybe This one looks like they might be positively correlated to some degree, but a lot of times you can see really clear patterns to understand what features that you have might be, redundant or include other features. And then if you specifically wanted to just look at a histogram, obviously pandas will allow you to do that, right? So this is effectively one of these plots that we've seen, but you just have a lot more options over exactly how it's shown here. So now I'm going to jump into the slides for a second, and then we'll come back and finish the second half of this workbook. And you should see the slide now. So we've done this get data part, and we've maybe started to creep a little bit into the prepare data part of the process. But now I want to just go over a couple different ways that you can prepare data really briefly. So I mentioned that you want to actually look at the data, but besides just seeing that there's missing data points, you want to decide how you're going to actually deal with those. Maybe the missing values are correlated with some other attribute, right? You might do a survey, and people who have higher salaries, for instance, wouldn't want to reveal their income on a survey. So you want to understand just removing missing values a lot of the time can introduce bias into your model. And there's a lot of different ways that you can deal with that we're not going to really dive into too much here. You could see this flowchart of a couple different ways that you can deal with that. Just to kind of give you some idea of how complicated or involved even the really small and obvious seeming parts of the process can be. One other topic that can come up is outliers. So sometimes you have the data for something, but it's way outside the range of what you see for anything else. So first you have to make decisions like, are outliers really a problem based on the kind of distribution of the data that you would expect? You want to make sure that you're ideally identifying outliers in some automated way, because you're going to want to be able to do that as you have more data and as you make prediction. So then you'll try to consider the cause of your outliers, and you can see here some of these different methods that you can possibly use to correct for it. But there's a lot of ways, and again, for each of these topics, we could easily dive in and do a 2-hour technical talk. And the last thing in data preparation that I'm going to touch on is the idea of feature engineering. So what feature engineering is that you're using your domain knowledge to create features that make algorithms work better. So maybe let's say you have timestamps for predicting flight delays, and hey, I want to use these and kind of, I expect there to be some patterns maybe on Mondays that there's more of a delay, or in the morning there's more of a delay. So you can initially consider just the hour of the day. Maybe you extract just the hour of the day out of the timestamps, or you can extract the day of the week out of the timestamps and try to use each of those as a feature. You can do things like bucketing, like if you have ages, having a different value for every age might not help the model. It might actually confuse the model. But putting it into a bucket of different age ranges might allow you to get more predictive power out of those. And another example here is latitude and longitude. So what this means kind of is latitude and longitude are numbers that in isolation, they don't necessarily give you nearly as much information as knowing both of them for a specific thing. So you might want to try to combine those into one feature so that your model considers it that way. And then besides just creating new features, you'll want to go and remove any features that you think are unnecessary, because they just create noise to your model and they can kind of confuse the model while it's trying to learn the important patterns. And this is where a lot of the art and the work of making a good model comes in. So the main takeaway for this is that data cleaning is really the key step to making machine learning algorithms work. So yeah, so I see in the chat some people are bringing up a bunch of other steps that you can do and that many times you should do before implementing a model, like data scaling. And that refers to things like maybe you're trying to build a model where you're predicting, like I said before, like real estate prices, one of your features might be the square footage of a house and the other one might be the number of floors, right? So if you had a entry where the number of floors was, 5, you'd be pretty surprised. That would be way outside your range, but you would expect square footage to be, 1,000 or a couple thousand, and that would be pretty normal in terms of the distribution of your data set. So to prevent your model from overweighting uh, square footage or those larger values, a lot of times you'll also want to do some scaling of the value that you have to get them all in the same range. And there's a lot of different approaches to that. And again, that's a little outside the scope of the talk, but it's definitely good to be aware of. So now we'll jump back into that notebook and we can go through the second half of the notebook, which is all about data preparation. So if you remember before, we had loaded in all the spy plane data that we had, and we just looked at it, but we haven't actually done anything yet with the data. So in this case, I suspect that there are some rows where there's missing piece of data. So what we can do is run this specific command, pandas function, which will show us if there's any nans, which are not a number. And this just checks in for any of them within a row. And you can see here that there's, like all of these records have nans. And in this case, because it's just 5 rows, we're just going to remove these rows from the data set. So that's what this command is going to do. We're just taking the same data frame as before, and we're dropping any rows with nans and saving that into our new data set. A good approach too, whenever you're cleaning data, is to try to always keep the raw data untouched, right? You want your process to be repeatable. So it's always good to build up kind of the code to go from your raw data to the clean data. And wherever possible, sometimes it can be too computationally expensive to do this feasibly, but wherever possible, you wanna, once you make any changes to your code, rerun that and go from your raw data back to your clean data again, so you know everything is in process the same way. So in the article that we source this from and in the GitHub repo, BuzzFeed used a bunch of information that they had from a previous story and gave the different planes that they were known spy planes or surveillance planes a label. So that's what we're pulling in here. So you can see the identifier for the plane, and you can see that it has this label that it is a surveillance plane. So in this case, we're going to use label data because we're doing supervised learning, and I'll go into that in a moment, depending what people's familiarity is with this. That might be a new thing. So we're going to take this, and what we want to do is first do some basic inspection, right? So we're going to look at it and see, all right, how many values do we have for different things? So of all of the data that they have in here, we have 97 of them are labeled as surveillance planes. We have 495 other, and then we have 5 others. So this is an example where you can check for things like data entry errors by looking at these kind of higher level summary functions. So what we're going to do is replace others with other because they should be the same. And then we're going to replace that and just update the value counts. So now you can see that we have the 97 surveillance planes and the other planes are all classified as other. And now to merge that with our existing data, we're going to run these pandas command, which is just a merge. If you're familiar with SQL, this is an inner join. So now you can see at the end, we have this class added to the end, and that's the column from before. And we merge those based on this plane identifier. One more thing that I'll touch on. So occasionally when you go to build a model, the data that you pull in is not something that could be easily fed to a model. So like here we have type, right? And you can see these are all kind of just a bunch of different strings. it can be really noisy or expensive to pass this. It's a lot of data to pass into a model for, when the model really doesn't care exactly what the letters are, just that it's a specific type. So in this case, we have 132 unique plain types in the data set. So one way that you can deal with this and make it more efficient to get this information into the model is to factorize. And what we're going to do with this is we're going to take that column, and I will show you what the outcome is. We come up with this factorization, which says that for each type, instead of having this string, we're just going to have a number, and it's going to be, there's going to be 132 different potential values of this number. So for each record, instead of passing, if the type is ship, instead of passing ship, we're just going to pass 0. And that gives the model the same information, but in a much more efficient way. And now we're going to take the new clean data that we just generated, and we're going to export that out to CSV. And now I'm going to talk for a minute about the actual model development process. So we've gone through getting the data, we've prepared the data, now it's time to finally build the model. So while this is often the most talked about part of machine learning, I hope that you see as we go through this, and based on what we've talked about, it's actually a lot of times a relatively small component within the scope of the entire data science and machine learning process, going from deciding what model to build, working with other shareholders, getting the data that you need, and preparing the data. So this chart shows some of the main branches of machine learning, really supervised, unsupervised learning, and reinforcement learning. It also gives further separation that you can see as you go into each one, and they split out. You can see some example use cases where you might use, let's say, regression or classification. And what we're specifically going to look at in this case is supervised learning. So what supervised learning means is that you're using labeled data to predict future outcomes based on past performance. So there's kind of the two categories of this, but the general way to know, kind of like the cheat sheet one rule check for if you're doing supervised learning is if you can look at your data set and one column is the answer, then you're doing supervised learning. So if you remember a few moments ago, we concatenated that surveil or other column to the end of our data set. So that is the labeled data, and that's what helps us. That's why we're doing supervised learning. So there's two main categories of supervised learning. The first is classification. And this is basically what category does this record fall into, right? In this case with email, is it a spam email? Is it not spam? For us, is this a surveillance plane? Is it not a surveillance plane? Whereas regression is you're looking at an entry and you're trying to predict some other value, right? So you have feature X or some set of features on the X-axis, and based on those, you want to predict what the price of the house is going to be. And we're doing classification, like I mentioned. But now that we've talked about data, we're going to talk at a high level about choosing an algorithm. So you've likely heard about regression. You've likely heard about classification, XGBoost, deep learning. And if you attended Josh's talk, you heard about AutoML and some other approaches of doing that too. But it actually can be a little bit of a struggle to choose the exact one. So you'll find charts like this one. This is from scikit-learn, which is a really popular Python package that's used for machine learning. And in general, you'll be able to narrow down your selection based on things like if you have labeled data, what kind of data you have, how much data you have, and some of the other limitations of the data, and especially things like how much compute power you have available, right? Some really good models can be very expensive to train. So you'll have to consider kind of all those things. But charts like this can definitely help. So while there's never one best algorithm for a specific project, and you're always going to want to do a little bit of trial and error with different algorithms available, In many cases, you can lean on existing work or resources like this to at least help you get started with a model that's probably a pretty good fit for what you're trying to do. So in this case, we're just going to pick one model. We're going to go with a decision tree. So what a decision tree does is it models a set of sequential decisions that ultimately lead you to some final classification. So here, the decision tree is, should I accept a new job offer? And the way this works is you have some data point that has a bunch of different features. And what you do is at each decision node, you basically just say yes or no for whatever your filter is, right? So maybe you have some salary filter and that tells you yes or no. And then you pass it down to the next branch. And then you go to the next node and you decide again, and then you decide which branch to follow. And ultimately, it should give you some final classification, right? If we pass here our 3 filters, then we're going to accept the offer. And if we don't pass one of our screening rules at a different node, then we're going to decline the offer. Each of the nodes where you end up with the final answer is called a leaf node. And this is kind of, if you think like a tree branch, right at the end is the leaf. So conceptually, it sort of makes sense. And typically, as you go further down the levels into the branches and nodes, the questions will get more and more specific, right? If you imagine, this is only 3 layers, but for an automated process, you might have, you can go very, very deep in terms of layers. You could have 50 layers that you're going to kind of exhaust a lot of the really easy wins in terms of questions in the beginning and have to start being creative with what the questions that are chosen. And these are all going to be chosen automatically depending on which implementation of the algorithm you use. And specifically what we're going to do is we're going to use a random forest classifier. So a random forest classifier is kind of the next level on top of a decision tree. So you can see what we're going to do is we're going to fit a bunch of decision trees, right? So this is a high level overview. Each of these is a different decision tree. So one of the trade-offs you're always going to have with modeling is between something called bias and variance, which I'm not going to dig into too much, but the idea is the more powerful and the more complicated you allow your model to be, the more likely that it's going to learn very specific things instead of learning things that can generalize. So one good solution to that is doing things like this, where you're basically doing like ensemble modeling between a bunch of trees. And each tree, this now lets you say, okay, we're going to have one tree. Each tree we're going to learn a lot of very specific things. So we don't have to worry about a specific tree capturing everything. But we're going to combine the predicted results from each tree. And you could do things like majority voting. You could take the mean. And we're going to use that to decide what the final class is. So this lets you capture really high level behavior or really complicated or complex behaviors to model, but also do it in a way where you're not overfitting to the specific data that you have. So now we're going to go back into the workspace. And now we're going to open up this second notebook. And this is called Random Forest Classifier. And again, the same, we're inside of a Jupyter notebook. So any cell that has code, just remember to run it by pressing Shift Enter before moving on to the next one. And that's what will let the code actually run. So the first thing that we're going to do is we're going to import the packages that we're going to use, and then we're going to pull in the data that we prepared in our previous notebook. So we're pulling in the same packages as we pulled in last time up here, but now we're also adding scikit-learn, which is a library with machine learning algorithms. That's where that flow chart that we looked at before came from. And libraries are great because they make it relatively cheap in terms of your time and effort to experiment with different models. And we'll see how easy it can be to kind of implement a model from one of these popular libraries. Now we're going to pull in the CSV from what we prepared, and you could see that relatively the same columns. and you can see this factorized type at the end. So like I mentioned, the random forest classifier is what we're going to build, and that is going to basically create a bunch of decision trees at training time and then output the class. The prediction is going to be the mode or the mean of all the individual trees. You can follow this link to see more about the docs behind how random forest classifiers work and specifically how they are implemented and work in scikit-learn. The first thing that we're going to do, now that we have an idea of what model we're going to use, we're going to specifically format the data for that model. So here the tradition is that X is the data that's going to be available at prediction time, while Y contains the label that's our actual output and prediction. So what we've done here is we've done another factorize, the same as what we did before, but now we're just doing it on this class column. So if you remember, all that should be in here is other and surveil. So these are just going to be values of zeros and ones, where Y says that it's a surveillance plane and 0 says that it's not a surveillance plane. Then we're also going to create our X. So we're going to drop all of the columns that aren't used for training. So this index at the beginning, we're dropping because that just kind of tells us which row we're looking at, but that doesn't provide any specific value to our model. We're dropping class because we don't want to tell, you never want to train the model with it having the answers, because then you give it the opportunity to effectively just memorize all the answers, and that won't generalize to anything else. So we're removing this, and you can see now this is the X that we're going to feed in. So we're going to say for every new plane record that shows up, we're going to take this effectively like a row of this data, and we're going to use it to predict a 0 or a 1 for a surveil or other. One thing that I mentioned, so along with the idea that you don't want to put the answer inside of the training data because the model will directly learn that, you also want to make sure that you're not capturing maybe some weird features of the specific data that you have. So something you'll always want to do when you make a model is, at a minimum, split it into some training and test sets. And what this means is that you'll train the model on just the training set, and here we're going to use 70% of our data for that purpose. And then you'll test the performance of the model that you've trained on data it hasn't seen before, and that's the remaining 30%, and that's the test set. So there's a lot of considerations when you split data into train and test sets. You want to make sure that you are doing it randomly, and there's some other concerns that you may have depending on what kind of data you have. So toolboxes like scikit-learn make it relatively easy with kind of these automated functions where you put in your X and Y, you put in some of the things that you care about, and then it will go through the process of building out these test and train X and Y sets for you. So we're going to split this, and you can see here, this is the size of the training data, right? So we have our 32 features, and we have here 415 entries. And for the test set, we have 178. So this matches our 30 and 70% of what this data is. Now we're gonna, before you train the model, right, you have to actually say what the model is. So we've talked about it being a random forest classifier, but you have to let scikit-learn or whatever packages you're knowing exactly what you want it to do. So the first thing we'll do, and this is another thing you a lot of the times will want to do during model development, is we're going to set the random seed. So when computers generate random numbers, right, they basically, there's a lot of approaches to it, but typically you have some really complex formula that every time that you run it, it gives you a number that like appears to be and is pretty random, but it's not perfectly random, and it follows like a deterministic process. So if you set the random seed, this means that if I did this and I pulled 10 random numbers, every time that I pull 10 random numbers after setting this, those numbers will be the same. So what this lets you do is make sure that you're getting repeatable results, and that improvements that you see in your model's performance aren't just a result of you getting a slightly better set of random numbers. So now we've selected the classifier, the random forest classifier we're going to use, and we've trained it. And you can see kind of how easy it actually can be to train a model. And we're just scratching the surface here, but just in this one block, we've gone from having our data to now having this SPY model object trained that we can then use to go make predictions. So we're going to use that to just show you what it looks like to predict some of the classes on our test data. And you can see here, most of the predictions, it predicted that of the first 10 planes, only the sixth one was a surveillance plane. And then you can also see, besides just doing this, so the way that we're doing this, if you remember, we have kind of when we did the factorizing, we have 0 and 1. So in this case, we basically just have one class, right? Because it's either like spy plane or not spy plane. But you can use this if you have multiple classes to see the probability that the model thinks that it's each class. So these should generally sum up to 1. And in this case, you can see that there's really just 2, right? The first one is the chance that it was not the first is the chance that it's not a surveillance plane. The second is the chance that it is, or the probability. And this one, you can see the probability is higher that it's a surveillance plane, so that's why that one was selected. So now we've done this, let's say we want to go look at our accuracy, right? You always want to know how good your model is. So here, I've just kind of manually written out this formula that you could use to check accuracy. And we have, all right, like, 95.5%, that looks pretty good. And we'll dive into this a little more in a moment. But one thing that I wanted to show too, again, just expressing the value of using existing packages, is that if we use, we already have this trained model and we have the data that we just use to predict. So if we want to just do the score, you can run a function like this, and then you don't have to worry about, debugging your code, or if you have some complicated metric, if you did it correctly, you know that you're using the one that's been tested and implemented in the package. And you can see here that we get the same value out, which is good. So now I'm going to talk a little bit about evaluating your models. And then the rest of this time is gonna all be hands-on inside the workshop after this. So with model development, we've gone through from getting data, we've prepared our data, and we've built a model. So, we looked at accuracy. So maybe we've started to touch on the idea of evaluating a model, but figuring out how good your model is can be pretty involved. So one takeaway is that you always want to use data to test your model. And I talked about this, but you want to use data. You want to make a model that is going to perform well on data it hasn't seen before, because that's how you're actually going to use it. And you want to try to make sure that what you use to evaluate this ultimately, especially in a business setting, is based on business metrics and things like ROI, as opposed to just looking at accuracy or core modeling metrics. These can be really good as you're going through the process of building your model, but ultimately you want to be able to tie them back to something that's actually valuable and demonstrably valuable to the business. And you'll also always want to think about, like, what is the cost or impact of a false positive or a false negative? So we used accuracy in the end of that last notebook. So we can dig into that a little bit, because the first thought people usually have is to look at accuracy. So in this case, let's say we had 100 patients and we want to predict which ones are disease-free. So one of them has the disease or the illness, and we do this test, and we find out that our model has an accuracy of 99%. So that sounds really good. But in fact, what this means is that the model actually is probably just predicting every patient as disease-free. So it's not very useful at all. One way that you can look at this stuff is something called the confusion matrix. So a confusion matrix is the summary of prediction results on a classification problem, which is what we're doing. So here we can see the counts of how many correct and incorrect predictions were made, both for the positive and negative class. In our case, positive is if it's a surveillance plane, and negative is if it's a normal class. And the name, confusion matrix, stems from the fact that it makes it easy to see if the system is confusing two classes or commonly mislabeling one as the other. And you can see that, if it labels a positive as a positive, that's good. If it labels a negative as a negative, that's good. And these are kind of the two types of error that you can get. So to add a little more on top of that, you may find that based on the problem that you're doing, that one type of error is more expensive than another type. So for classifying spam, you may find that if you classify spam as a regular email, it just gets left in your inbox, and we've all had that experience. It's kind of annoying. But the flip side of this is that you classify a regular email as spam, and then it gets moved out of your inbox, and that's a much bigger downside. So we'll want to make sure to tune our model where maybe we get a little more false negatives at the expense of getting less false positives. And the two metrics that we use to kind of codify this or do it in a rigorous way are precision and recall. So precision is how precise our model is, how good it was at identifying only the relevant positive samples. And you can see here the formula for this. And here we're looking just at what the model predicted was positive. A perfect precision score of 1 means that every email that was predicted to be spam actually was spam. But it doesn't say that we caught all the spam email in the data set. Recall captures the other side of this, which is how much were we able to capture all of the relevant positive samples. And here we're looking at the actual positive values. And a perfect recall score of 1 means that every spam email in the data set was identified. But again, it doesn't say, every email could have been labeled as spam and we would have perfect recall. So you usually want some blend of precision between the two, right? Like I said, if you just look at recall and you have a value of 1, that may just mean that your model classifies everything as the 1 set. So F1 score is something that's pretty commonly used, and you can see the formula for that down here. And this is a harmonic mean of the two. So a complete failure is 0, a perfect score is a 1. And this is used instead of taking the average of the two because it punishes extreme values and it kind of pushes both scores to be pretty good. And this can be especially useful when there's an uneven class distribution. And the reason that is like we saw before, if 1 out of 100 of your values are the class that you're looking for, you'll get 99% accuracy even if your model hasn't learned anything. So that's where things like this can really be valuable ways to understand how your model is working. Okay, now we're going to jump back into the workspace, and we'll go through a couple notebooks talking about how you can evaluate and then how you can improve your model. So briefly, we're just going to codify what we talked about in the slides just now with different ways to evaluate your models. If you open notebook 3, we're going to do pretty much the same process we did in the last notebook. We're just condensing it into a couple cells, so we don't have to go through it in too much detail again. We're pulling in packages, we're pulling in all the data, doing all the same processing and training. And now we're going to talk about evaluation metrics. So last time we used accuracy, right? And accuracy is just the number of correct predictions over the total number of predictions. And this is not a great measure in cases where the classes are imbalanced like they were in our case. And here you can see our accuracy seems pretty good just looking at it as a raw number. But we can actually go ahead and generate directly the confusion matrix. And here we're just putting these values into a new data frame to help us visualize it. And you can see here are the predicted surveillance planes that were also actual ones and the predicted other that were other. So this actually looks reasonably good. given that we haven't really done any model tuning yet at this point. We can go ahead and calculate both precision and recall. And precision is, again, how correctly we identify only the relevant surveillance planes. And our precision was actually pretty high in this case. And our recall was also reasonably high. So this lets us know that even with all the default options, without doing any tuning, random forest captures a lot of what we care about from the data. And then we can go ahead and capture the F1 score, which is the harmonic mean of both of these. And again, this is what you'll use when you want to balance a bolt. And you can see this is 0.8. And again, that was on a range from 0 to 1. So this is a reasonable starting point. Now we'll open up page 4. And this is where we're going to start talking about hyperparameters and tuning. So in this, again, we're going to start off doing pretty much what we did, the same 2 cells as what we had in the last notebook. And what we're also going to do at the bottom of this, you'll see some code run when you start this cell, is we're going to install a specific package. So sometimes when you're running your code, right, you might find that you need, you want to run some new type of model. And some people who have used Jupyter maybe aren't aware that you can actually install packages from within Jupyter. So if I had tried to import this Bodo3 package before installing it, we would get an error that it's not available. But you can actually just do this pip install after an exclamation point, and that will let you install usually the package that you need, assuming you have all the permissions. And you can ignore some of the warnings that come up. Then we're going to read in our data again. And now we're ready to start talking about hyperparameters. So what hyperparameters are all the different settings of an algorithm that you can adjust to improve performance. So these are things that you're going to set before you train the model. In some cases, like what Josh touched on in his AutoML talk, you'll automate the process of doing these hyperparameters. But first, it's good to sort of understanding the trial and error process and how it's working on the back end. So we can see the effects of altering specific hyperparameters on compute time and performance by increasing the number of estimators. And what that means here is in our random forest, we have a bunch of decision trees. So we're just going to increase or change the number of decision trees and see how that affects our compute time and the result that we get. So here we have the number of estimators equals 10. That means that we're going to use 10 trees. And if we run this, we see our F1 score is 0.77, and that this took 17 milliseconds to run. One benefit of random forests and decision trees is that they can be very efficient and very scalable. And that's one of the reasons that we picked it for this workshop. So sometimes you may do this, right, and it could take a couple hours to train models with different hyperparameter values. Now we're going to try the same exact model, and remember we set our random seed up here, so we should all that should be changing is just this one value, and we're changing it from 10 to 100. So now our F1 score went up from 0.77 to 0.82, but you can see also the wall time increase. So this illustrates that trade-off that you're always going to have between putting more computation time into your model and the result that you get out. That doesn't necessarily scale forever, but a lot of the time, the compute power you have available is going to be one of the constraints. Someone had asked in chat, what does random seed apply or imply? So I had touched on this a little before, but I guess to be more concrete about it. So there's when you call for a random number, in this case from NumPy or from a computer, it typically runs some algorithm to generate the next random number from the random number and some intermediate or like hidden values that you have. So what a seed does is it means you're taking this number and running some function on that to set all of those hidden values to a certain state. So if you do this, you'll always get the same number the next time that you call back to NP random. And if you call it 20 times, there are going to be 20 seemingly random numbers. But if you do that and then you rerun this random seed and call 20 numbers again, they'll be the exact same numbers as what you saw before. So we changed one hyperparameter here, but there are a lot of other hyperparameters that we haven't explicitly referenced. So scikit-learn gives you this option to get params, and this will show you all of the hyperparameters that are available or the options for that model and what the values of those are. So you can see things like here, we've set the number of estimators back to 10. So you can see that the number of estimators here is 10. You could see some other features, and we're actually going to get into those now. So what we're going to do here, I thought this might be fun. We'll see how this works. I haven't actually tried this before. An online workshop is kind of a new experience, I think, for a lot of us. So we're going to try to do a hyperparameter tuning competition, and we'll take let's see what time. We'll take 10 minutes or so to go through this. So what we're going to do is we have this sheets set up down here, or this cell that's going to allow you to change these 5 different hyperparameter values and then rerun the model. Here you can see some information on what the 5 hyperparameters available are. And some of them, right, are just integers. Some of them you have to use these specific values inside of the single quotes. So once you maybe take 10 minutes or so, you'll be able to change the numbers down here. When you run this, it will show you your F1 score. So what we're going to try to optimize for is F1 score, but we'll also look at precision and recall just in case maybe some of the F1 scores are really high to get an understanding of what's going on. And then whenever you think you have a result that you want to submit, and you could do this as many times as you want, you just run this cell. And whatever you use for the newest, whatever model you had just run before the last time that you hit this is what's going to show up in the leaderboard. You may occasionally get an error out of this cell, but if that's the case, just run it again. I'm not 100% sure what causes it, but you shouldn't have to worry about that. So, all right, I will give everybody about 10 minutes, and you can put any questions in the chat, or if anyone runs into an issue, and you're free to pretty much do whatever you would like to try. Just try to keep it to these 5 hyperparameter values, so that because this is what we're going to track in the leaderboard, so that we can sort of see what everybody's strategy or output was and how that affected their performance. So maybe what we'll do is I can run the leaderboard in another minute or two, and then we can take a couple more minutes and see once we have seen what maybe the winners or the higher performing models are. Everyone can go back for 2 more minutes and get 1 or 2 more tries. Has anyone, I saw someone say there's a parser error, but has anybody been able to run that code cell at the bottom? I'm assuming they mean this one. Yeah, I think the, okay, yeah, so I'm sorry, Bodo 3 was installed. Oh, interesting. Yeah, so Stephen had just mentioned Bodo 3 was missing in the first cell. So if that's the case, you can also add to the bottom. You'll just want to run !sudo pip install Bodo 3. And then when you run this other cell, if you get an error, it's possible it's from this last line, which just shows you the data that you submitted. It's not actually necessary. So if that's the case, you can always put a £sign in front of that to comment that line out. Yeah, so I'm not seeing, maybe can everybody just run a couple times in a row that last leaderboard cell? It looks like for some reason a couple of them maybe were empty. We can do this. Hmm. I can try to debug this for another moment. Does anybody, I guess if someone thinks they have a really good result, they can run, they can put maybe what their F1 score was in the Zoom chat, and we could try to do it that way. Yeah, I think what's happening in this case is for some reason, maybe some of the files got uploaded empty. .875 looks pretty good. Let's see, maybe we can kind of brute force our way through this. There you go. Okay. So we can see some of our top 5 right now. Let's see if we can see more. All right, nice. So we have a couple people who have actually pretty similar results in terms of F1 score, 0.875, and what's pretty interesting actually is to see, especially between, like, there's kind of these 2 categories, right? One of a lot of estimators with really low depth, and this is kind of the number of layers in your trees, versus a really small number of estimators that are a lot deeper. Has anybody tried a really large number? Like, does maybe someone can try a really large number of estimators and like a combination of both of these? We can give people another minute or two to see if they can top one of these. But yeah, 0.875 is pretty good. Yeah, so interesting. Yeah, thanks, Stephen, for pointing that out. So in this row, actually, somebody actually did 10,000 estimators with a max depth of 50. So it's also possible that this started to really overfit some of the data. So there might be a nice balance where both of these are on the higher end, maybe like 1,020 or 1,015 or something like that could be a really good combo. But yeah, it's always so usually what you'll want to do in this case, right? There's many of us kind of trying different values of inputs. You'll want to kind of try a lot of different models and a lot of sets of hyperparameters, and being able to look at them in some way, either like a table or a plot like this, to kind of track and see patterns like this, and what you've done can be really helpful. And in this case, it could be a red herring, right? But it looks like if we kind of increase the number of estimators a little from this one and increase the max depth from that one, just from my very human pattern recognition kind of best guess, that we might see a slightly better increase. Let's see what time it is. All right, yep, I'll wait about 1 more minute for anyone who wants to submit a score to the leaderboard, and then we'll see how we did. And another interesting takeaway too in this case is the ones with the highest F1 score. We mentioned that a lot of times you use that to kind of think about trade-offs, where maybe you might expect that there'd be one with really high precision and one with really high recall. So you'd use F1 as like kind of a tiebreaker. But in this case, actually, the ones with the high F1 score had higher precision and recall, or at least the same. So I'm going to run this leaderboard again. It's possible I'll have to change a couple numbers if we run into an error. Yeah, so it looks like we're pretty much the same. So yeah, I see some more on here that are in that like 1,020 range. Uh, but yeah, I mean, sometimes you really can end up with just kind of a sweet spot for different hyperparameters that you have. And keep in mind here, we have 5 hyperparameters. So if you think like a really, really basic optimization problem, right, is you're trying to find the minimum or in your minimum error, or in this case, the maximum for your F1 value. So you might have like, let's say 2 features, and then what you're optimizing in could look like a bowl at a really basic level. And you know, you want to get down to the bottom of the bowl. But in reality, once you have a lot of features like this, it's unlikely that the actual thing that you're optimizing in looks like a bowl anymore, right? It might be more like an egg crate or really corrugated or some complex shape in some way. So there can be very local solutions that give you really good fit. Um, you know, so you can't just look at kind of 2 extremes and assume that the value in the middle is going to be really good. But yeah, definitely interesting results. So now that we've had some experience manually changing hyperparameters, uh, there's obviously a lot of ways to automate this, right? So you can imagine that if you spent all day trying different hyperparameters, it's likely that you would have a better result in the end. Maybe you just randomly hit on the right one. So in Josh's previous talk, he talked about AutoML, and there are some a whole gamut of solutions for how you would deal with this, right? You could do it at a really low level. You could do it at a very high level, where you can even use machine learning to choose the next hyperparameters that you're going to use. But in this case, we're just going to talk about one really basic approach. So this is in Notebook 5. And here we're going to pull in the same packages and the same data from the previous notebooks. And we're not going to pull in the model because, again, we're going to split the data up, and then we're going to use some more automated hyperparameter tuning methods to tune the model. And here what we're going to use is randomized search. So one of the most basic approaches that you see to hyperparameter tuning is grid search. So what that means is, you know, we have 5 hyperparameters here. Yeah, we have 5 hyperparameters. This is still one. We're just adding an option to the end. And you say, for each of my hyperparameters, here are the available options, right? So the minimum sample split can be 2, 5, 10, or 20. There's these 3 options for the max number of features. And what grid search does is it will search every possible combination of those parameter lists that you give it with all the steps. One downside of that, if you have a lot of hyperparameters and you want to search, you don't want to miss a really good local solution, is it can just be really expensive and take a really, really long time to run. A benefit is that it's parallelizable, but it can still take a long time to get a solution if you have a large search space and an expensive model to train, and you have a lot of steps that you want to search on. So one solution to that is doing the random grid, random search. So what you do is you take the grid and then you're randomly selecting some points. So we're not selecting or testing everything. We're just randomly searching across. This also does some other things like cross-validation, which we're not going to get into now, but just good to be aware that you have tools available to do a lot of this stuff. So we'll just run this first cell and declare our grid. And then we're going to use this to search for the best hyperparameters. So this right now is going to run a bunch of tasks, which is basically trying a lot of different possible combinations of those parameters that are along the grid that we declared up here. And this is going to be a relatively small search set. You know, you could imagine this is automated, right? So if you add a lot of grid points, you could let this run for 4 or 5 hours and do a pretty comprehensive search of your space. But just for the purpose of this conference talk, we're going to search over a small area, and then we'll see if the result that we get is better than what we manually found or not. And it might not be. So that'll be, you know, certainly the more computation time you're willing to spend on tuning hyperparameters, the more likely it is that your result's going to be really good. So here is just a bunch of information about the model that was tuned, but what we actually care about is what the best parameters that we found were. So here's what we found. So 1442, 10 samples split, square root and none. Right, 1442, square root 10, and false. So yeah, so this is, you know, pretty close to what we had over here, which makes sense, right? Because you're probably gonna hit one of the basins of attraction that we ran into with manual hyperparameter tuning. And now we're gonna feed those parameters back into the model and make a new random forest classifier with that, and then make some predictions, and we'll see what our actual accuracy was. So here we have our F1 score. Let's increase that a little bit. But yeah, it looks like it wasn't as good as some of the ones at the top of our leaderboard. Oh, did I? Interesting. Oh, maybe it's been rounded earlier on. That's surprising to me. But yeah, I mean, either way, the ones that we saw in the leaderboard were 875. So if it was better with the rounding, it would have at least shown up as 0.9. So yeah, good job to everybody on the leaderboard. It looks like actually a lot of the people that did the manual tuning were able to do better than the automated tuning was able to do in about a minute or so. Yes, humans have defeated the machine. So now the last thing that I want to show you is how you would actually go and make a model out of this, or not a model, an app. So we have a lot of the code prepared for this already. So we're not going to talk about, you know, programmatically how you would build an app. Effectively, it's just some code that you write in whatever language you want, right? You know, Dash or Shiny, and you start up some kind of server, and it is running a copy of that code, and then you go to a specific endpoint, and that lets you interact with whatever app you've written. You know, Flask, Dash, and Shiny are kind of the three most popular ones. And you can do really cool stuff with that, and they abstract away a lot of the parts of the app process, the same way as packages did, like scikit-learn for machine learning. So if you want to go and publish a model, you can actually. If you go back into your project in Domino, that'll be in the other tab. And then you'll go to this publish option. And then you'll come into app. And I had published an app already, just it might take a minute or two to start up, and I wanted to have one ready to show you. But there should be an option here to start your app. And once you click on that, you'll give it a name, and you can leave all the options how they're set. And then you can hit start on the bottom right. And that'll take a couple minutes to spin up that app, and then you'll be able to click on this view app button and interact with it. And what this does here, there's a ton of apps that you could build with this data, but this is like a pretty basic one just to sort of show the value you can do is, yep, oh, someone had asked how to create an app again. So if you go into the project and you click publish on the side and you go into the app option, then there should be a start app or create app. I don't remember exactly what the button says, somewhere over here. And once you do that, you just put a title in, and then at the bottom right, I believe, there's the launch button, and then you'll have to wait 2 minutes for it to spin up. And what that is doing from the Kubernetes level, since we, just to tie it back to the infrastructure, is it's creating, you know, spinning up a Docker container, putting your code inside of it, and then putting that all inside of a pod. And then Kubernetes figures out where on the machines you have the available capacity to run your app. So what this app actually does is let us look through a big list of planes, right? We could see like all the planes in our data set. And it shows you two things. It shows one, the prediction uh, of it being a surveillance plane, and this is based on the model that you built. And you can also see actually the raw data down here. So some of them you may have to zoom in a lot to actually see the points of the plane, but you can kind of see where the plane was. And this is a large majority of the information that the model had when determining if it was a surveillance plane or not. And some of these, right, will just be really dense plots. And I don't remember. Yeah, for instance, you may see planes that took more, uh, maybe what you would expect as a traditional path for a plane. And you can also see those in here. So this kind of makes it interesting to see, you know, when you look at this flight path, does that look like a surveillance plane, and how does that match up with the model that you just trained? So you can certainly continue to click around in here. I'll give everybody a minute in case the models are still spinning up, or the apps, in case they want to look at those before I conclude with the rest of the slides. And some of these have like just one data point, so it may be really hard. Oh, here you go. Yeah, but you could, I mean, it is pretty interesting to be able to go and see, and this is all public data of plane flight paths. So you can kind of look this up and see just the value of an app is largely that it allows people who may not be comfortable directly interacting with your code, or if you just give them a big spreadsheet with a bunch of these probabilities in it, uh, you know, this makes it much more tangible for maybe a customer or a business user who's outside of the data science team to be able to interact with the work that you've done. So having an easy way like in Domino with just a few buttons once you have your code set up to host and run your apps can be really valuable to be able to share and collaborate the results that you have. I'm going to switch back to the slides, but feel free. There's just a couple slides left in the talk, and then you can come back and play around with this app. Ultimately, we're going to shut this deployment down, but we'll leave it up for a little bit to give everyone time to explore the app. Okay, everyone should see the slides again. So just a couple quick slides to kind of tie everything together. So we've now stepped through the whole process of model development. We'll send you some links. I believe Josh had mentioned maybe in the chat that we'll email slides out to the emails that you entered. If anyone wants a copy, you can feel free to ignore those. And we'll also send you a link. I'm going to put a copy of this project. We have a try Domino deployment. So this deployment specifically for this workshop is going to be taken down probably sometime later today. But if you want to play around with Domino more, or if you want to play with these notebooks more, we'll send you the link to that project so you can always sign up there or go directly download them and play with them on your own time. Sharing and collaborating is kind of the last part of this process, and we touched on this a little with the app. But the better you can do this, kind of the more rewarding that your projects are going to be, right? You put all this work already into developing a really great model. You know, you don't want to have this funnel or this kind of blocker at the end in terms of how you can share that with people. So really thinking through and being active about collaborating with other people on your team and across your organization, and being able to share the work that you've done is really important. The one thing I'm going to touch on that I've seen that gets dropped a lot of the time is at the end of a project, you want to purposely wrap up the work that you've done so you can archive everything that you've learned and you can carry that forwards. And here's just a couple of key points on that. So make sure that you save everything needed to go back and revisit your experience. So we mentioned the idea of trying to go back and run code from 3 months ago on your laptop, and then you run into some weird issues and you have to spend all day debugging. And then you're also not even sure if the new result you get is the same as the original result that you got. So just some of the things you want to preserve are any intermediate results, obviously the code and the data, and the environment. So the environment is what we saw in those compute environments, and this is something that Domino makes pretty easy, is that we version control all of the code, the data, and the environment that you use, and your results, to make it pretty easy to go back and see, hey, 4 months ago when we worked on that project, what exactly was it that we did that got that result that I remember? And the reason you want to do this, um, and that you want to be kind of vocal about it and make sure you have an organized process, is that it prevents you and other people on your team from having to learn the same lesson multiple times or go back and recreate work. And this really brings us back to the original goal, which is understanding like the entire life cycle of like a machine learning or data science project, and how that ties back and can impact your business. So I hope that everybody learned something, and I really appreciate you spending 2 hours with us on this call. Yeah, and I hope that you learned something that you can take back to your work. And we have about 5 minutes for any questions that people have in the chat. So let me see, scroll. So one of the questions was about student access to Domino. Yeah, so we'll send out that try link, and there's definitely limits there in terms of like the size of the hardware tiers that are available, but that's enough for you to be able to play with the interface and kind of see what Domino is all about. And that's at try.dominodatalab.com. So for really, really imbalanced data, there's a lot of research that kind of goes on and what the best ways to deal with that is. And I am not up to date on like what the current best practices around that. I know a lot of the times you could do things, like resampling, which kind of allow you to synthesize more of the data that's imbalanced. Maybe you mix together some of the records that you have within your imbalanced data set to synthesize more. You do like tiny transformations to that data. And that can help train your model to recognize those patterns, but not be fit to the exact data points or records that you have in the really small data set. Somebody asked what level of math would be required for this approach. Is there a specific approach that you're asking about, or more the type of modeling that we did over this workshop? Assuming that it was the general work that we did in this workshop, uh, you can really approach this with a wide range of math expertise, right? There's all these great packages like scikit-learn that allow you to abstract away a lot of the math to do this process. As always, the more you put into it, the more you'll get out of it, right? So if you take time to develop a lot of the expertise of what's going on behind the scenes, that will help you understand how to go find and implement some of the most state-of-the-art algorithms that are being used by people. So that's kind of a fuzzy answer to your question, but there's not some clear cutoff. You can definitely build machine learning models with minimal to no mathematical knowledge, but you will likely get much better results as you learn a lot more about what's going on behind the scenes. And I'm seeing some questions about this. So just to reiterate, we will send out a link to anybody that signed up for this within the Domino. We'll send out a link to where you can see this project with all the notebooks, and we'll also send you a copy of the slides. And for Vivek, so he asked a question if business leaders will need to understand machine learning models at some level. And definitely there is a lot of value in that, right? Sometimes maybe a stakeholder, you won't have enough buy-in or they won't have enough background for you to really walk them through how a model works. And that's why one of the things that you think about when you build a model, besides how predictive it is, what kind of data you have, and what kind of computational resources you have, one thing that you think about is interpretability, right? So something like decision trees, we didn't get too deep. There's definitely more you could learn about it. But even if you didn't know about random forests before, you probably have a rough idea of what the model is doing behind the scenes, even based on those 2 slides and 15 minutes or so of playing with the algorithm. So there can be a lot of value in picking models that are really interpretable and explainable to people, to kind of get buy-in, and so they understand what's going on with this model that they're going to hand off their decision-making process to. All right, yeah, I'll give people another minute, see if there's any other questions, and then for anyone that's checking out now, thank you very much for attending this talk with us. Yeah, I'm glad you. Thanks, Kushal. I'm glad you enjoyed the workshop. I think there's a question about model interpretability. Uh, so again, like many of the topics that we've touched on, this can be really deep. And sometimes, if you get into models like neural nets where they're really not interpretable for the exact things, if you go look directly at the model, there's even fields of training models to make other models more interpretable, right? So you have some model, you train some model on that, and then you use that to like give you an interpretability layer. But kind of my point was that a lot of the times there's going to be some trade-off, and hopefully this isn't, you hope that you can find some solution where this isn't true, but there's always going to be some trade-off between using a more complex model that captures a lot more of the behaviors that are going on in your data, and that will give you a better result. And on the other side, having a model that's straightforward and explainable enough, like maybe decision trees, just straight decision trees, that doesn't give you quite as good a result, but is really easy to understand what the model is doing. So if you imagine something like, what's a good example? So one example is if you're trying to make a self-driving car, one of the problems that comes up is thinking about like pedestrian prediction, right? You want to obviously track where people are and pedestrians and where they're walking, but there's always some uncertainty about what direction they're going to go. So one way that this was done a while ago was you would just look at kind of the vector of like what direction, how fast they're walking there, and you would just take some normal distribution around that. So you say, in general, I assume people are going to keep going in the same direction. And that seems like a lot of the time it's going to be pretty good. There's obviously cases like, maybe kids playing, and they're more likely to kind of have like erratic movements, or they, go chase a ball in the street, or if it's, if somebody's hiding in a bush next to the road, you might think it's more likely that they're going to run across the road or something along those lines. There actually was a case where a company trained a really, really powerful predictive model that did a better job of predicting where pedestrians were going to be, but it ended up not being used for a really long time because people were concerned that, hey, with this old model, like I know if someone is, hiding behind something, getting ready to like run in front of a car, that's a failure mode for that predictive model. Whereas with this new model that might be a lot more accurate, I have no idea what the failure modes are. And that exposes you potentially to a lot more risk. So you may find that stakeholders are less willing to implement some non-interpretable model, or it's harder for you to get buy-in that your model is going to be safe or whatever use you're going to use it for, if they can't interpret it or you can't explain it. So I am going to have to jump off to go get ready for another call, but I really appreciate everybody's time, and I hope that you enjoy the rest of the conference and the rest of your week. See you.